For example 2, this one's a little bit different. You'll notice that you're not actually given an angle in this case, you're actually given a ratio. And it says if angle A is between 0 degrees and 360 degrees, and sine of angle A is equal to -1/2, determine the exact measures of angle A. Because what you'll notice here is that I'm actually given a ratio. Because I'm given a ratio, this means that I could potentially have more than one angle that satisfies the conditions here. Okay? And because I have more than one angle, or because I have a negative ratio, I can determine which quadrants this would fall in. So if I look at the cast rule here, my ratio is negative, which means I need to look at the third and fourth quadrants because that's where sine is negative. So my angle A value will be in quadrant 3 and it'll be in quadrant 4 as well. Now this is similar to what we looked at in lesson 2, where we would have to draw a terminal arm diagram in both of these quadrants. So hopefully you recognize the difference. When you're given the angle, you know which quadrant the angle falls in. When you're not given the angle and you're given a ratio, your angle value can fall in more than one quadrant. Okay, so in this case it's going to fall into 2 quadrants. It's going to fall into quadrant 3 and quadrant 4. So there's my terminal arm diagram. And what I know based on this ratio is that the ratio of my opposite and hypotenuse sides, because this is sine, is -1/2. So if I actually draw a triangle here, what this means is that my opposite side is -1 and my hypotenuse is 2. Remember, your hypotenuse can't be a negative answer. So that'll be +2 and this will be -1. Okay, and this makes sense for it to be negative because you're actually going down 1, and that makes sense with the -1. Now, what I'm trying to figure out is what the angle is in quadrant 3 and what the angle is in quadrant 4. So let's examine our diagram here. I know that I have a special triangle that has a side length of 1 and a side length of 2. So if I look at my special triangles here, this one has side lengths of 1 and √2, which eliminates the idea here. But this one has a short side length of 1 and a hypotenuse of 2, which is similar to what we have here. So if I actually try to rotate this, I sort of have something that looks like this, with a hypotenuse of 2 and a shorter distance of 1. So what that actually tells me is that this side here is most likely √3. Same thing on this side. Well, this would be -√3 because it's left √3. And so what that tells me is that this related acute angle here is 30 degrees for both of them. And that makes sense because that's my smaller angle, that's my smaller side, and that corresponds in this triangle. So what I found so far is a related acute angle in quadrants 3 and 4. Now what I could do is solve for the actual angles in each of these quadrants. In quadrant 3, this is more than half a rotation, so I'm expecting the angle to be between 180 and 270. And so in quadrant 3, angle A, and I'm using angle A because that's the angle measure we're looking at. We're not looking at theta. So angle A in quadrant 3 would be equal to 180 degrees plus the additional 30-degree rotation. So angle A would be equal to 210 degrees. That's my first angle. And in quadrant 4, this angle is a little bit short of a full rotation. So remember, looks like that. And so a full rotation would be 360 degrees, and this is 30 degrees less than that. So I get an angle of 330 degrees instead. Okay, so there's your 2 angle measures, and again, you can plug it into the equation here and find sine of 210, you'll get -1/2. Find sine of 330 and you'll get -1/2 again. Okay, for the final question, this is an application question that relates to special angles. And it says a ship is tied to a dock with a rope of length 10 meters. At low tide, the rope is stretched tight, forming an angle of 30 degrees with the horizontal. At high tide, the stretched rope makes an angle of 45 degrees with the horizontal. How much closer to the dock horizontally is the ship at high tide than at low tide? And then determine an exact expression. Now, the first time you read a question, you get the gist of the concept. And so this deals with a ship that is tied to a dock with a rope. And depending on whether the water is at high tide or low tide, so depending on how high the water is or how low the water is, the actual angle that the rope makes with the horizontal can vary. So what I'm going to do is I'm going to draw this picture. So let's say this is the dock, and there's a rope that's connecting it to the ship. And here's my ship. That's as good as it's going to get. And it says that it's making a 30-degree angle with the horizontal. So let's say that's 30 degrees. And I'm just going to make that into a triangle because we are looking at special triangles. This is the unit on trigonometry. And one of the other piece of information I know is that this is 10 meters. Okay, so this is at low tide. So at low tide, it makes an angle of 30 degrees. At high tide, it makes an angle of 45 degrees. So I'm going to draw another picture with a dock. And this time at low tide, at high tide, I have my ship. And this time it's making an angle of 45 degrees with the horizontal. So here's my ship. And then here's the right angle that I'm going to make into a triangle. Okay, so there's the picture that I have in there. Okay, now the other thing I want you to notice is that this rope is still 10 meters. And what we're trying to figure out is how much closer to the dock horizontally is the ship at high tide than it is at low tide. What you'll notice here is that at high tide it is closer versus at low tide where you see that the distance a little bit longer. And I know sometimes pictures can be deceiving. In this case I tried to draw it as accurately as I could, but please be careful. Sometimes if your diagram is not accurate, you might confuse yourself. Okay, so I'm looking for a horizontal distance here and the horizontal distance here, and trying to figure out how much closer this distance is compared to the first one. So maybe I'll call this D1 and this D2. Okay, now how am I going to solve for this, and how am I going to get the exact expression? Well, let's take a look at what ratio this is actually creating. So if you remember from grade 10, what you did is you looked at the angle and the sides that you are given and looking for, and you came up with a trig ratio. We're going to do the exact same thing here. So here's my angle that's given. I have an adjacent side and I have the hypotenuse. And so the ratio that would compare all of these is cosine. So what this means is cos of 30 degrees is equal to the adjacent side, which is D1, over the hypotenuse, which is 10. Now I know how to solve this, but I only know how to solve this using decimal answers. Another way to solve this is to recognize that the cosine of 30 degrees is an exact value that you can determine from your 30, 60, 90 triangle. So if I look at my 30-degree angle here and I look at the ratio of the adjacent and hypotenuse sides, I can rewrite the cosine of 30 degrees as root 3 over 2. Now I'm not dealing with trig anymore, because on the right hand side I just have a number and a variable that I'm solving for, and all I need to do at this point is rearrange the equation to solve for d. So I can do that by either cross multiplying to get 2d1 equals 10 root 3, and then I can divide both sides by 2 and I get d1, and I'll show you that actually. So if I divide both sides by 2, I get d1 is equal to 5 root 3. So what that means is, and this is in meters I believe, so what that means is this distance here is equal to 5 root 3 meters. Okay, now let's do the same thing for the other side. We're going to look for the second distance. There's my angle that's given. That's my adjacent side, my hypotenuse side. And adjacent and hypotenuse is related through cosine. So I'm going to look at cos of 45 equals d2 over 10. And then again, cos of 45 is something I can find the exact value of. And again, that's the whole idea here. If it asks you for an exact expression, then that means that you should be able to use the special triangles to get an exact ratio. And so in this case, again, cosine of 45 degrees, I can figure that out as an exact value. All I need to do is find my 45-degree angle in the special triangles, and the ratio of the adjacent and hypotenuse sides gives me 1 over root 2. And then again, it's just a matter of simplifying this and trying to find the exact value. So I'm going to cross multiply again, and I get root 2 times d2 equals 10. And then I get d2 equals 10 divided by root 2. So again, I should show you all my work. So I'll just do that. So to get the second distance by itself, and again, you can use a and b, x and y, whatever works for you. I just happen to use d for distance. These two cancel out, and I get d2 equals. Now the problem in this case is that I have a root 2 in the denominator, so I'm going to rationalize the denominator. This goes back to one of your older units. And so what I end up getting is 10 root 2 over 2, which I can simplify to 5 root 2. Okay, and that's in meters again. So there's the second distance. Now because I'm trying to figure out how much closer the 45-degree angle would end up being compared to 30, I'm going to find the difference between the D2 and D1. And so the difference would be, or the total distance would be, five root 2 minus 5 root 3. Okay, so the longer distance, sorry, I did it the wrong way. That's the longer distance, that's the shorter distance. So if I look at the difference between them, I have 5 root 3 minus 5 root 2, and this is in meters. So therefore, the ship would be 5 root 3 minus 5 root 2 meters closer.